Inside the nose compartment of the B-17 bomber, where the temperature has plummeted far below freezing, the bombardier is at work. His mission is not to destroy an entire city, but to achieve a pinpoint strike on a single factory shed, avoiding civilian casualties. He carries the weight of the moral high ground. He leans over the device that the American command dubbed the equipment of God, the Norden Bombsight. This was no mere optical sight. It was a complex analog computer the size of a radio. Its development and production cost the country over $1.5 billion and was shrouded in such absolute secrecy that crews swore to destroy it with their lives in case of a crash. For the critical 60 seconds, the bombardier must manually synchronize its gyroscopes and optics with the aircraft's speed, wind direction, and ballistics. In the final moments, the Norden takes control of the aircraft itself, overriding the pilot to ensure an absolutely straight and stable bombing run. This is the culmination of a technological faith that promised surgical precision. But as he tries to lock on to the target through the freezing, cloud-choked European sky, a brutal truth emerges. Norden demands perfect sunlight and absolute visibility, conditions that almost never materialize over German targets. This is the story of the most expensive military myth of World War II, the promise of technological infallibility that collided with harsh combat reality, proving that in actual warfare, pinpoint accuracy was not a breakthrough, but a top-secret failure. The Norden Bombsight was the creation of Carl Norden, a meticulous Dutch engineer who had emigrated to the United States. Norden viewed his work with an almost religious intensity, believing his invention held the key to transforming the very nature of warfare. His fundamental goal was not merely to increase accuracy, but to provide a tool for the morally superior conduct of combat. He believed his device could ensure surgical precision, enabling armies to destroy enemy military assets, such as specific factories or bridges, while intentionally sparing surrounding civilian populations. This profound ethical conviction became the philosophical core that underpinned the machine's development and its powerful propaganda narrative, the ability to hit a pickled barrel from 20,000 feet. Throughout the 1930s and into the early years of the Second World War, the United States government committed an unprecedented fortune to the Norden program. The cumulative expenditure for research, development, specialized manufacturing facilities, and training reached a staggering $1.5 billion in contemporary value, a figure that rivals the initial costs of the more famous Manhattan Project. This massive financial allocation was a clear reflection of the military leadership's absolute, unwavering faith that this singular piece of equipment was the technological linchpin necessary to guarantee victory in the aerial campaign over the European theater. The military establishment intentionally cultivated an almost mythological reverence around the bombsight, often referring to it with hyperbolic and spiritualized nicknames. The most famous moniker, the equipment of God, or sometimes the blue box, served a profound psychological purpose. This high esteem was critical for instilling a supreme, almost ideological confidence in the young bombardiers operating the device. This psychological conditioning was essential to counteract the immense terror, pressure, and distraction they would inevitably face during a bombing run conducted under heavy enemy fire. Security surrounding the Norden bombsight was perhaps the most stringent enforced by the United States government until the atomic bomb program was fully underway. Every single individual who came into contact with the device, from the engineers building it to the airmen using it, was required to participate in a solemn ceremony and take a formal, sworn oath of secrecy. This pledge legally and ethically bound them, underscoring the extreme strategic value placed on preventing any details of its intricate technology from reaching the hands of the enemy powers. The fear of the Norden's technology being captured led to extreme operational mandates. Every heavy bomber, including the B-17 and B-24 fleets, carried a specialized defense kit. This usually included a small, but powerful, thermal incendiary grenade or a hammer, placed near the instrument. In the event a plane was severely damaged or forced down in enemy territory, the bombardier's final, mandatory act was to physically smash the optical glass and drop the grenade onto the machine's delicate internal mechanisms, ensuring its complete destruction and incineration before capture. The official specifications and marketing claims presented by the military asserted that the Norden Bombsight could reliably achieve a circular error probable (CEP) of just 100 feet when dropped from the operational altitude of 20,000 feet. The CEP measures the radius within which 50% of the dropped munitions should land. This breathtaking promise, the equivalent of hitting a small vehicle from 5 miles up, provided the essential technical and political justification for adopting the deeply risky and costly strategy of daylight precision bombing over hostile airspace. The complex, finely tuned electromechanical nature of the bombsight placed immense demands on the manufacturing process. The device required components crafted with extremely tight tolerances, often using precious materials like brass and high-grade aluminum. Its assembly had to take place in specialized cleanroom environments to prevent dust or minor imperfections from disrupting the delicate computing function. Maintaining this industrial standard, while simultaneously scaling production to meet the massive demands of a global conflict, presented constant quality control and logistical challenges. Before the introduction of the Norden, the British Royal Air Force had largely conceded to the relative safety of large-scale night bombing, focusing on area saturation. The Americans, however, embraced the Norden as the technical catalyst that would allow them to conduct their preferred strategy, daylight precision bombing. This fundamental strategic divergence was entirely rooted in the belief that the bombsight's pinpoint capability rendered the dangers of unescorted daylight raids acceptable and tactically superior. The irony of the absolute security measures was that the secret had already been lost years before the war began. The German spy Hermann Lang, a naturalized citizen who worked as an engineer directly at the Carl L. Norden Incorporated factory in New York, successfully accessed the complete schematics. Lang meticulously copied the detailed blueprints and delivered them to German intelligence. This fundamental compromise occurred before the United States formally entered the war, rendering all subsequent oaths and destruction protocols essentially moot. Beyond its direct military application, the highly secretive and high-tech nature of the Norden bombsight made it an invaluable asset for domestic wartime propaganda. The narrative of its infallible accuracy was continually used to assure the American public that their massive financial and human investment in the war was justified. This story helped bolster public support, encouraged participation in war bond drives, and sustained morale by presenting the war effort as a technologically and morally righteous crusade. The fundamental purpose of the Norden bombsight was to instantaneously and continuously solve a complex trigonometric problem known as the triangle of velocities. This triangle consisted of three vectors: the velocity of the aircraft, the velocity and direction of the wind, drift, and the calculated velocity and trajectory of the bomb as it fell. The Norden's complex internal gearing system was designed to resolve these forces in real time, predicting the exact future point on the ground where the bomb would land, an astonishing feat of analog computation for its era. At the mechanical heart of the Norden lay a set of highly sensitive gyroscopes. These were the essence of the precision myth. Once the gyroscopes were spun up to their operating speed, they provided an utterly stable, immovable platform of reference, regardless of the aircraft's pitching, rolling, or yawing motion caused by turbulence or evasive maneuvers. This stability was crucial. It gave the bombardier the critical, but fragile, illusion that the target remained perfectly still in the optical sight, allowing for fine-tuning that would otherwise be impossible. The bombardier initiated the process by looking through the instrument's optical scope, manually locating the target on the ground. Once found, they would use a series of fine adjustment knobs to align the crosshairs with the target point. This action mechanically fed initial information, the elevation angle and the drift, into the synchronous computing elements. This was the moment the Norden transitioned from being a passive viewing instrument into an active calculating machine. One of the most radical features of the Norden was its direct integration with the aircraft's automatic flight controls. For the final, critical 30 to 60 seconds of the bombing approach, the bombardier would electrically couple the bombsight to the aircraft's autopilot. During this period, the bombardier, not the pilot, had primary control over the aircraft's direction and stability. The bombsight's continuous calculations automatically fed corrections to the rudder and ailerons, ensuring the aircraft followed the mathematically perfect flight path required for a successful bomb drop. Wind drift was the enemy of accuracy, especially at high altitudes where jet streams could be unpredictable. To compensate, the bombardier had to manually input observed wind speed and direction into the Norden via dedicated dials. The computing section would then incorporate this vector into its running calculation, constantly adjusting the predicted impact point and, consequently, the aircraft's heading to fly a complex crab angle that perfectly offset the drift. The actual moment the bombs were released was governed by a precise electrical trigger generated by the Norden itself, eliminating human reaction time error. As the airplane flew, the machine continuously calculated the exact point of the release line, the moment when the geometric relationship between the falling bomb's trajectory and the aircraft's speed was perfect. When the aircraft reached this instantaneous point, the circuit closed, and the bombs were automatically dropped from the bay. The Norden was an engineering marvel of its time, utilizing a complex architecture of interconnected gears, cams, and shafts, the synchronous mechanism. This purely mechanical system was capable of performing multiplication, division, and integration through the physical rotation of its components. Every fractional turn of an adjustment knob translated into a corresponding change in the relationship of the internal mechanisms, creating a dynamic, constantly evolving mechanical model of the aircraft's flight environment. Although the computing was mechanical, the bombsight relied heavily on high-precision electrical power to drive the gyroscopes and the synchronous motor that performed the calculations. The system required a significant amount of time, typically 15 minutes, for the gyroscopes to spin up to their operational speed and stabilize fully before any calibration or accurate use could commence. This warm-up period was a non-negotiable requirement for achieving any semblance of precision. The final bombing run was an exercise in controlled, mechanized flight. Once the bombsight was coupled to the autopilot, the bombardier focused intensely on maintaining the target lock, using delicate fingertip adjustments. The successful execution of the mission required the crew to hold this perfectly straight, predetermined course, regardless of the psychological terror or the physical buffeting caused by defensive fire. This rigid adherence to the Norden's computed path often made the aircraft a predictable and vulnerable target. Because of its extreme mechanical complexity and delicate internal tolerances, the Norden bombsight demanded dedicated, specialized maintenance. The entire unit had to be rigorously calibrated and synchronized before every mission. Any minor flaw, a piece of dust, a misaligned gear, or a slight electrical fluctuation could translate into an error measured in thousands of feet on the ground. This necessitated an entire logistical chain of highly trained technicians separate from the usual aircraft ground crew. The single greatest operational failure of the Norden bombsight lay in its inherent and rigid dependence on visual confirmation. It functioned only as a sighting device, requiring the bombardier to maintain clear, direct visual contact with the target for the entire duration of the final synchronized run, typically 45 to 60 seconds. Over the European theater, especially over industrial targets in northern Germany, cloud cover and persistent overcast conditions were the norm. On most days, visibility was completely obstructed, rendering the highly precise, multi-million-dollar analog computer utterly useless. The Norden was designed and tested primarily under ideal laboratory conditions, failing to account for the brutal environment of high-altitude combat. At the typical cruising altitude of the heavy bombers, around 25,000 feet, temperatures routinely plunged to 50 degrees below 0 Celsius. This extreme cold caused the precision lubricants within the bombsight's intricate gear system to thicken or even freeze. The resulting friction introduced major, unpredictable errors into the continuous calculations, often causing the delicate mechanisms to seize or operate sluggishly. The final bombing run required the bomber to fly a perfectly straight and level path dictated by the bombsight's autopilot. During this critical minute, the aircraft was highly vulnerable to defensive fire, commonly known as anti-aircraft artillery bursts. The continuous concussion and shrapnel hits created severe vibration throughout the aircraft structure. This physical jarring immediately disrupted the fine balance of the Norden's stabilizing gyroscopes and could throw the delicate crosshairs off target by hundreds of feet in an instant, nullifying all prior precision. Operating the Norden required the bombardier to make extremely delicate, almost microscopic adjustments using fine-tuning knobs during the final approach. This task was complicated by the harsh environment. Bombardiers were encased in heavy, restrictive flight suits and thick gloves, and were forced to breathe oxygen through clumsy masks. The reduced dexterity and physical discomfort compounded by the altitude and stress made the requisite fine motor control virtually impossible to maintain, leading to inevitable human error being factored into the mechanical precision. The engineers calculated for prevailing winds, but at high altitudes, the existence and intensity of the jet stream presented an unforeseen variable. These fast, high-altitude air currents could change speed and direction rapidly and were impossible to measure accurately in the few minutes available for the Norden's calculation input. A simple 10-knot error in wind velocity input, compounded over the long free fall of the bomb, could result in the bomb missing the target by several hundred yards. The synchronization process demanded that the aircraft adhere rigidly to the path dictated by the bombsight for the final approach. Pilots were forbidden from making any evasive maneuvers. This created a highly predictable and linear target for enemy fighter aircraft and anti-aircraft crews below. The Norden's quest for mathematical perfection sacrificed the safety of the bomber and often resulted in increased aircrew losses, a heavy cost for theoretical accuracy. The Norden Bombsight calculated the trajectory based on the assumption that the bombs used were uniform in shape and weight, possessing perfect aerodynamic qualities. In wartime reality, mass-produced bombs often had slight imperfections, inconsistent fins, or were dented during loading. These subtle variations in aerodynamics meant the actual trajectory of the bomb often deviated unpredictably from the precise path calculated by the analog computer, introducing unavoidable random error. The Norden was a laboratory-grade instrument, but it was subjected to battlefield conditions. Due to the high tempo of operations and the secrecy surrounding the device, the specialized, clean-room level of maintenance it required was rarely available at forward operating bases. Units were often serviced hastily, exposed to dust and grime, or stored without adequate protection, leading to mechanical wear and calibration drift that rendered the theoretical precision moot long before takeoff. The final phase of the mission introduced a unique command conflict. The bombardier effectively took control of the aircraft via the bombsight's autopilot link. Many pilots, accustomed to autonomous command, resented being overridden by an analog machine and a younger crew member. Any slight disobedience or premature override by the pilot, driven by the instinct to evade fire, could instantly spoil the precision of the bombsight's meticulous calculations. The true performance of the Norden was systematically obscured by the chaotic nature of combat. It was difficult to assess which missions failed due to the machine's mechanical limitations, bad weather, or simply the destruction of the aircraft before the bombs could be dropped. The enormous human and material cost of the daylight bombing campaign made it politically and strategically inconvenient for military command to admit that the central piece of technology was failing to meet its core promises. By 1943, the operational reality of the Norden bombsight could no longer be hidden by the cloak of secrecy. Field statistics revealed that the machine was failing miserably to meet its publicized promise. Records showed that under combat conditions, only approximately 20% of the bombs dropped landed within the general target area, and a staggering 70 to 80% fell more than a quarter mile away from the intended aim point. This data completely undermined the notion of pinpoint accuracy. Instead of the promised 100-foot circular error probable, the operational CEP for the majority of the air fleet stood closer to 1,200 feet. This vast discrepancy meant that the bombsight, rather than guaranteeing surgical precision, was delivering a wide pattern of destruction. The primary function of the machine was relegated to providing only a marginal improvement over older, visual-only sighting methods, effectively turning the $1.5 billion investment into a highly complex placebo. Faced with undeniable statistical proof of the Norden's failure and the crippling loss rates of bomber crews, military command was forced to initiate a fundamental change in doctrine. The lofty goal of precision bombing was quietly abandoned in favor of area saturation bombing. The new strategy dictated that instead of trying to hit a single factory building, formations would aim to destroy the entire industrial complex or, often, the city district surrounding it. To salvage some semblance of efficiency from the Norden, a new tactic was deployed: the use of a lead bombardier. Under this system, only the lead aircraft in a massive formation was required to utilize the Norden for the final, precise calculation. Once the lead bombardier released his ordnance, all subsequent aircraft in the formation would simply drop their bombs when they saw the lead ship's bombs fall, regardless of their own Norden readings. This simplified the process but amplified the catastrophic results if the lead bomber was off target. The perpetual issue of European cloud cover necessitated a complete reliance on non-visual bombing alternatives. This led to the rapid introduction and widespread deployment of the H-2X radar system. The H-2X, a ground-mapping radar, allowed bombardiers to target large geographic features, coastlines, rivers, major cities, beneath heavy cloud cover. While the radar system was inherently less precise than the Norden in clear weather, it offered reliability that the optical bombsight could not, as it was immune to atmospheric conditions. Throughout the war, a profound disconnect existed between the internal reality and the external narrative. The aircrews knew the bombsight rarely worked as promised, often calling it the Spies automatic sight, referencing a competitor, out of dark irony. Yet, the military and the press continued to celebrate the Norden as the technological marvel that justified the sacrifice. This sustained myth became more valuable to the war effort than the actual machine itself. The daylight bombing strategy, driven by faith in the Norden, resulted in appalling crew loss rates, particularly in 1943. The command structure was forced into a difficult position. They had to maintain the strategic commitment to daylight bombing to justify the massive investment and losses already sustained, even after recognizing the Norden's technical failure. The solution was tactical adaptation rather than strategic retreat. When the Norden was deployed in the Pacific Theater against Japanese targets, its operational efficiency faced a different set of challenges. High humidity and the vast distances over water created new maintenance difficulties. Furthermore, the reliance on high-altitude precision bombing was often rendered irrelevant by the introduction of low-altitude, area saturation raids and the eventual use of nuclear weapons, sidelining the Norden in the final phase of the conflict. The statistical failure of the Norden fundamentally shaped post-war military doctrine. The Air Force learned the harsh lesson that achieving true pinpoint accuracy required technology far superior to analog mechanics. This realization spurred massive research into digital computers, inertial navigation systems, and advanced radar, leading directly to the development of cruise missiles and guided munitions decades later. The ultimate takeaway from the Norden saga was the realization that in complex, unpredictable combat environments, overly intricate analog mechanical systems are destined to fail. The bombsight's complexity, its dependence on perfect internal synchronization and perfect external environmental conditions, was its downfall. The lesson paved the way for the simpler, more robust, and ultimately more effective digital computing solutions that would dominate military hardware in the coming decades. Immediately following the conclusion of the war, the Norden bombsight was rapidly and unceremoniously phased out of service. Despite its massive investment cost and decades of development, the rise of more reliable radar systems and early electronic computing meant the analog mechanical Norden was instantly relegated to technological obsolescence. Its retirement was swift, reflecting the military's eagerness to move past the failures and limitations exposed during combat operations. The rigorous security measures that had dominated the Norden program were mocked by the public confession of Hermann Lang. The American engineer, a dedicated spy, revealed that he had delivered complete schematics and detailed blueprints of the bombsight to German intelligence years before the United States entered the conflict. This revelation confirmed the ultimate irony. The secret that aircrews were willing to die to protect was never truly a secret at all. A further twist of historical irony was that the stolen Norden blueprints, once delivered to the German High Command, were never effectively utilized. German engineers, already struggling with their own complex military hardware and prioritizing other projects, viewed the Norden as overly complex and difficult to mass-produce under wartime conditions. The machine that cost the United States billions proved too fragile and demanding for the enemy to replicate, highlighting its fundamental flaw. Although technically flawed, the Norden Bombsight fulfilled an indispensable psychological function. It provided the aircrews, who faced terrifying odds, with a tangible symbol of technological superiority and hope. The belief in the equipment of God sustained morale during periods of catastrophic loss, giving the young men a sense that their dangerous missions were justified by the promise of precise, militarily effective results. The inventor, Carl Norden, lived long enough to witness the end of the war and the complete retirement of his life's work. He remained deeply religious and was reportedly disturbed by the extensive civilian casualties caused by the strategic bombing campaigns. Though his machine was credited with saving lives through its intent, its actual combat performance contradicted his original vision of surgical warfare. The development and refinement of microwave radar, particularly systems like the H-2X, ultimately sealed the Norden's fate. Radar allowed bombers to target objectives through thick cloud cover or at night, offering the crucial element of operational reliability that the visual Norden could never achieve. The military prioritized consistent effectiveness over theoretical, clear-weather perfection. For several decades after the war, the full truth about the Norden's dismal combat statistics remained highly classified or obscured by the initial propaganda. As a result, many popular histories and public accounts continued to celebrate the bombsight as the technological wonder that had decisively guided the air campaign. The myth of its accuracy persisted long after the machine itself had been scrapped. Even after the war concluded, the government ordered the destruction of most surviving Norden units to prevent any possible lingering leak of analog computer technology. Those few complete units that survived were preserved in museums, often under tight controls. This institutional secrecy, which defined the program from its inception, lingered decades after the threat had vanished. Despite its failure as a precision bombsight, the technological principles developed for the Norden program were not entirely wasted. The advancements made in its highly stable gyroscope and the continuous, dynamic calculation of motion contributed directly to early research in inertial guidance systems, the technology necessary for navigating missiles and space vehicles decades later. The history of the Norden bombsight serves as a profound historical lesson against placing absolute, centralized faith in a single, unproven piece of technology. The machine's failure demonstrated that the most sophisticated piece of equipment is only as good as the chaotic environment in which it operates, highlighting the necessity of robustness, simplicity, and adaptability over fragile, laboratory-grade complexity in combat.